Welcome to The Explainer. Today, we are diving deep into the heart of piston aircraft engines. We're going to look at the two main ways they get their fuel, the old-school carburetor and the more modern fuel injection. This is a classic tech showdown, and it has huge implications for every single flight.
So, if you're a pilot, a mechanic, or really just any aviation geek, this is a core question. The system you have completely changes the game. It affects everything from engine power and how much fuel you burn, to the cost, the complexity, and, most importantly, your safety.
Okay, so let's set the stage for this showdown. Just think of it like this. In one corner, you've got the carburetor. That's your classic, super reliable workhorse. It's simple, it's cheap, and it just flat out gets the job done. And in the other corner, you have fuel injection, the modern, high-performance system that's all about efficiency and raw power.
All right, first up, let's break down the system that was the absolute standard for decades. It's powered countless aircraft with its incredibly simple and effective design, the classic carburetor.
At its core, a carburetor has a beautifully simple job. It's kind of like the engine's bartender, mixing the perfect cocktail of fuel and air. It gets this combustible vapor all ready to go in one central spot before sending it on down the line to each of the engine's cylinders.
Now, what's so cool about this is how it all hinges on this neat little piece of physics called the Venturi effect. See, as air gets squeezed through that narrow tube, it speeds way up, and that causes the pressure to drop. That pressure drop is so strong, it literally sucks fuel out of a little chamber, turns it into a fine mist, and mixes it right into the air. It's just a really elegant, self-regulating bit of engineering.
So, right here is the classic trade-off. The carburetor's beautiful simplicity. That makes it cheap to build and way easier to fix. That's a huge pro. But that exact same simplicity is also its biggest weakness. It can't really guarantee that every single cylinder gets the perfect fuel-air mix, and that hurts your efficiency. And it has a fatal flaw. It creates the perfect conditions for engine-choking ice. We'll get to that.
Now let's flip over to the modern solution. Fuel injection was basically engineered to solve the carburetor's biggest problems, and it does that by taking a much more precise, much more sophisticated approach.
So unlike a carburetor, there's no central mixing bowl here, no way. Instead, a pump pressurizes the fuel and sends it through lines directly to each individual cylinder. The fuel and air only get mixed together at the very last second, right before they go into the combustion chamber.
And this shows just how much more precise this method is. A regulator is constantly measuring the exact amount of air coming in and tells the system to deliver the perfect dose of fuel to match. Then, an injector nozzle sprays that fuel as a superfine mist right at the doorway of each cylinder. It's incredibly accurate.
So what's the payoff for all this fancy tech? Well, you get more power, and you sip less fuel, because every cylinder is getting that perfect mixture. And that scary carb ice we talked about, it's gone. But it's not a perfect system. It's more expensive to maintain, and it has its own unique little headache, something called vapor lock, which can make restarting a hot engine a really frustrating experience on a summer day.
Okay, this brings us to the single most critical difference between these two systems. And for a pilot, this can absolutely be a matter of life and death. We need to talk about icing.
This is the fact that catches so many new pilots completely by surprise. You do not need freezing winter weather to get carburetor ice. In fact, some of the absolute worst conditions for it are on mild, humid days.
So how on earth is that possible? Well, remember that Venturi effect? The rapid expansion of air and the evaporation of fuel can cause the temperature inside the carburetor to plummet, sometimes by as much as 60 or 70 degrees Fahrenheit. So yeah, on a 70-degree day with high humidity, you can easily be well below freezing inside that carb, building up ice that will choke your engine.
If you're the pilot, the first sign is subtle, but it's unmistakable. A gradual, unexplained loss of power. You'll just see your RPMs start to sag, or your manifold pressure will begin to creep down, even though you haven't touched the throttle at all.
The fix is simple. You pull the carb heat control. This sends hot air into the carburetor to melt the ice. But, and listen to this, here is the terrifying part. As that ice melts, your engine starts ingesting water, and it's going to run even rougher. It'll cough and sputter and shake, and every instinct you have will scream that you've just made the problem worse.
And this right here is a crucial, life-saving warning that you'll find in countless accident reports. Pilots panic when the engine runs rougher, and they push the carb heat back in, thinking they're fixing it. But what they're actually doing is letting the ice build right back up,
often leading to a complete engine failure just moments later. You absolutely must ride out that rough patch.
So, while fuel-injected engines are totally immune to that specific kind of internal ice, they aren't completely risk-free. They can still get something called induction icing, where ice forms on the outside air filter or the intake, just like it would on a wing. That's why they have an alternate air source to pull air from inside the cowling if the main intake gets blocked.
So, after going through the mechanics, the performance, and the really critical safety factors, what's the final verdict? What's the main takeaway for the person sitting in the cockpit who's responsible for the flight?
Well, this final chart gives us a really clear at-a-glance summary. The carburetor is simpler and cheaper, right? But it's less efficient and carries that really significant internal icing risk. Fuel injection gives you better power and better efficiency, but it comes with a higher cost and more complexity, and a much lower but still not zero risk of induction icing.
At the end of the day, the question isn't really just about which technology is better on paper. The single most important thing is for a pilot to deeply understand the quirks, the procedures, and the failure modes of the specific system they are flying. Whether it's the classic workhorse or the modern performer, it's that mastery of the machine that truly ensures a safe flight.